Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 391, Differential Equations. Last time we were talking about higher order differential equations, so let's jump back into that. Pretty much, it refers to differential equations of orders higher than 2, right? So we went through how to solve second order linear differential equations. And we saw all the methods that could apply to them. We saw ways to find homogeneous solutions. We saw ways to find particular solutions. The homogeneous solutions is using that method that has 3 cases based on the solutions of the quadratic. And the methods that we looked at to find particular solutions was variation of parameters and undetermined coefficients. We basically want to extend these ideas to higher orders. So if we have differential equations of the nth, where the highest derivative is n, where n is representing some number higher than 2. So it could be a third order, a fourth order, a 20th order, something like that. Looks like this. We want to be able to solve that. Of course, we focus first on the homogeneous case, and more than that, we focus on the homogeneous case with constant coefficients. Once we understand how to deal with those cases, we can move on to bigger, better, badder cases. All the things that were true for second order linear differential equations, analogous statements are true for these guys. I mentioned these in some boxes, what the solutions would look like, how many of them there are, all that good stuff. How to a generalization of Abel's formula, generalization of variation of parameters, undetermined coefficients also generalizes very nicely. And essentially the strategy for how to solve these equations also generalizes very nicely. So we're just going to assume our function that solves the solution is an exponential e to the rt. You plug this into the differential equation. It gives you a characteristic equation which you can solve. Now, that characteristic equation is going to be a polynomial of degree n. And in general, those guys are harder to solve, to put it mildly, right? So it's, in fact, once your power gets higher than 5, it's actually impossible to solve these by a standard formula. And sometimes you can't even find a solution in functions that we know how to actually write down and express. So yeah, it can get quite hairy. However, a lot of times with higher order coefficients, higher order or higher degree polynomials, there are some strategies that we can use to actually use what we learned from lower degree polynomials to apply to those guys. These are the guys that you would be tested on, that you'll see in class, and that's what we started talking about. So some special cases are the following. We looked at a case where it was a higher order, but you can kind of think of it as a lower order because the powers actually relate to each other in ways similar to how powers relate to each other in a lower order. So for example, for a quadratic, we know that the highest power is double the next highest power, and the next highest power is going to be 0. And so we can essentially think of any polynomial that has that kind of pattern in the powers as a quadratic, even though technically it's not a quadratic. The same strategies that work on a quadratic will work on those guys. And so we can use that and solve it. We did an example here. Another special case is when our special factoring techniques would work. Difference of squares, sum of, or difference of cubes. Those are these guys right here. And we did a couple of examples where we actually used that. So in this example, we used the sum of cubes. We're actually going to see another way to solve that particular kind of example. We use the difference of squares to solve that. And here we use the fact that we recognize this as we use factor by grouping for this one. The next special case was we can use binomial expansions just by realizing, knowing what Pascal's triangle looks like and realizing that our coefficients have that kind of pattern. We use that kind of pattern to solve this higher order ODE, which was a third order. And that's where we kind of stopped. We are going to pick up here now. And I had asked you guys to actually try this on your own. So hopefully you actually tried that. So let's just make a note here, started here on 1st of July. Our final is at the end of this month, and not even all the way at the end of this month. We're almost at the home stretch. Well, in the grand scheme of things, not really, but time-wise, yeah, like in like 3 weeks, we're gonna be done. So we have a lot to get through theoretically. So hold on to your seats, kids. Okay, so we are going to look at special case 4. This is using long division and the rational roots theorem. I'm not really gonna explain to you how to actually do long division again. I would expect you guys to remember how to do that. Hopefully you do. So the factor theorem says that if we have a polynomial and if we plug in a number, we get 0, or we find a root of that polynomial, then x minus that number must be a factor. It must mean that we can factor the polynomial, and one of the factors look like x minus c. So what you can do is once you plug in c, that factor becomes 0, and then the entire polynomial gets wiped out. So we've used that intuitively a lot, but the fact we actually do know that by the factor theorem. There's a theorem that tells us that's how a polynomial would behave. There's also the rational roots theorem. It says if you have a polynomial and an nth degree polynomial, and if it has rational roots, then they will have to be of this form. You can try factors of the constant term and divide those by all possible factors of the leading term, plus or minus that, and this will give you all possibilities for rational roots of the polynomial. It's not saying that you're guaranteed to find a root like this. It says if a rational root exists, that's what it's going to look like. It's possible that your polynomial does not have rational roots, and so this theorem would not take effect. It would just be not engaged at that point. With the help of long division, we can actually use the above theorems to actually factor some polynomials. So we are actually going to do that with these guys right here. Let's move some of these out the way though. And hopefully you try this. Let me move these out the way. Give me a second. I put them back in the way so that when I did the PDF printout, you guys would see them. But as for right now, I do not want them in the way. Hopefully that grabbed everybody. What? What? Okay. This should grab everybody. So hopefully you guys actually tried them. So you can, while I'm cleaning up a bit here, just pull out the work that you did and you can compare it to what I'm doing. The differential equations part of what we're doing isn't very different. The difference here comes from the fact that our polynomials are a little bit harder. It's harder to find the roots of the polynomials that we're concerned with. All right, so this was the first one. Now, this isn't a differential equations example. It's just me wanting to remind you how using long division to factor a polynomial would look like. So I just want you to solve for the R here. And you can, of course, imagine that this came from some higher order, in fact, specifically a third order linear ODE. You can imagine that this would be the characteristic equation of y triple prime minus 3y double prime plus y prime plus 5y equals 0. That would be the characteristic for that. How would you go about doing this? Well, by the rational roots theorem, let's call that RRT. Now, because we're tight, we can call them by a pet name. Rational roots theorem. I'm going to refer to this as RRT. I don't think I'm going to refer to the factor theorem, but just in case, let's call that FT. By the rational roots theorem, possible rational roots are, well, it could be a factor of the constant term, which is 5. So there are really only 2 factors, 1 and 5. And the factors of the first guy, the leading term, well, that's just 1. The factors of 1 are 1 and 1. So that would be the denominators. And you can take plus or minus of these. So the possible, or let's say potential, rational roots are, well, you can have 1, you can have -1, you can have 5, you can have -5. Now, I am going to use the factor theorem. Using the factor theorem, we can discover a root by plugging in to get 0, and this will imply r minus what we plugged in is a factor. So you go into your r cubed minus 3r plus 3r squared plus r plus 5 equals 0, and you start to plug in these numbers at random. So if you plug in 1, you'd realize that you'd get 1 plus 1 plus 5, that's 7 minus 3. That would not work. What if I plugged in -1? This would be -1 minus 3 minus 1. Well, that's -5. Plus 5 equals 0. It turns out that -1 works. So you would say, note, r equals -1 works. This means that r plus 1 is a factor by the factor theorem. So this means that I can actually go to my original guy and I can actually divide him by r plus 1. And I will get a polynomial as a result, and I will have 0 remainder. So this is r cubed minus 3r squared plus r plus 5. So now, of course, we apply the long division of polynomials. R into r cubed goes r squared times r gives me r cubed, r squared times the plus 1 gives me plus r squared. Subtract everybody. Of course, my r cubes now will cancel. And then here I have minus 3r squared minus r squared, so I get minus 4r squared. Then you repeat. R into minus 4r squared goes minus 4r. Minus 4r times r gives me minus 4r squared. Minus 4r times 1 gives me minus 4r. I'm going to subtract that from above. This r comes down. And so now I have plus, these guys will cancel. Then I would have plus r plus 4r. This gives me 5r. Repeat the process. R into 5r goes 5. 5 times r gives me 5r plus 5 times 1 gives me 5. And now you'll realize you end up with 0 here, and then you stop. Now you should get a 0. Otherwise, it's not a factor. Or you made a mistake. So double check your work because you should actually get 0. Once you actually plug in the number and you get a 0 up here by plugging in one of these potential rational roots, if you get a 0 up here, you definitely should get a 0 right here because there should be no remainder. Basically what that now means is that you can factor this polynomial right here as this guy times that guy. And again, not going to take the time to explain why that is. You can watch my 195 videos in case you forgot. So this means that my r cubed minus 3r squared plus r plus 5 can be written as r plus 1 times r squared minus 4r plus 5. And I have now started to factor this guy. Now I check, can that be factored any further? R plus 1, it looks like r minus 5, r minus 1. Wait, does that doesn't factor? All right, because I have to get a positive 5. If I read that correctly, yes, I should get a positive 5, which means that doesn't really factor. So this means r equals minus 1, or r equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So this is going to be 4 plus or minus, I can factor 4 from under the radical. That would be 2 when I moved it out. Then I'd be left with 4 minus 5. So I'd get 2 plus or minus I. Oh, you just typed the answer. Okay. And Incha has the answer. So here it didn't come from an ODE, but yes, if this did come from an ODE, those would be the roots. And those would be, it would be, so if this came from y triple prime minus 3y double prime plus y prime plus 5y equals 0, the solution would be y is equal to c1 e to the minus t plus c2 e to the 2t cosine t plus c3 e to the 2t sine t. So yes, but that's how you'd actually go about finding the roots. That's how you'd go about factoring and then finding the roots. So that is the power of the rational roots theorem. So you'll notice that if you look at this and try to factor it, it has 4 terms. So you would think factor by grouping, but factoring by grouping doesn't obviously work out here because of the minus 3 and the positive 5, right? You wouldn't, if you factor pairwise, you're not going to be left over the same thing. You won't have a common factor to pull out. So factoring by grouping doesn't work here, at least not directly. You'd have to figure out a way to get it to work, which it's actually easier, I think, to actually do the rational roots theorem. So that's using the rational roots theorem to solve for that. Let's actually solve some ODEs. So there we go. Hopefully you guys actually got that. What do we think is the answer? Give me some predictions here. Anyone do example 7? And what did you get for the answer to example 7? Just type your answer so I know you did it. So that when I do it, you can't just be like, oh yeah, that's what I got for the answer, and you did. You didn't actually do it. It's probably taking a long time to type. Anyway, I'll jump in and start because there's a lot of stuff I want to talk about after this section, and I'm hoping I get to it. I really want to get to it. So I don't really want to slow things down too much. So if you can type in your answer before I get to my final answer, I guess that'll be fine. I'm just going to jump in and try to start doing it. Because again, in principle, it's not like I'm teaching you anything new at this point. We're just applying things that we might have forgotten from pre-calculus class to the concepts that we've learned in this class. So it's not really anything new to teach you, really. I'm just putting some things together that, in theory, individually, we all know how to do very well at this point. Now we're just doing them together. So let's actually just, yeah, this would lead to the characteristic equation r cubed plus 10r squared plus 29r plus 20 equals 0. You notice it doesn't really lend itself to factor by grouping or anything like that very nicely. So at this point, I would go with possible roots. The factors of 20 are 1, 2, 4, 5, and 20 itself. The factors of the original is 1. So those are all the possible rational roots. And now I'm going to try to actually get a 0 here. Node r equals something works. I want to say something. So does one, definitely none of the positive numbers are going to work because I'm just going to be adding up a bunch of numbers and I'm not going to get 0. So maybe a -1. So if I take a -1 for r, I would get -1 plus 10 minus 29 plus 20. Does that actually work? Yeah, that works. -1. -1 works. Awesome. First try. Okay, so now this means that r plus 1 is a factor, which means I should be able to divide into this this cubic here. So this is r cubed. And remember, for this, you have to leave a placeholder for all lower powers. So even if there's no lower power, leave a space for it. So if there was no r term, for example, I would just write here 0r to leave a space for it. And so now I go through the long division process. R into r cubed goes r squared times that, r cubed plus r squared. Subtract. Then I would have here 9r squared. Then r into 9r squared goes plus 9r, 9r squared plus 9r. Subtract. Move this down. I would get 20r. R into 20r goes 20. Here I get 20r plus 20. Subtract. Move this down. 20 minus 20 is 0. So I know I did this correctly. And so it means I can factor these guys into, let me put the chat box out of the way here. Means I can factor these guys into my r cubed plus 10r squared plus 29r plus 20 equals r plus 1 times r squared plus 9r plus 20. And then I can see if that factors further. I think 4 and 5 would work. So this is r plus 1, r plus 5, r plus 4. And so that leaves us with the roots. R equals -1, r equals -5, r equals -4, which means our solution C1e to the minus t plus C2e to the minus 5t plus C3e to the minus 4t. That's our solution. Hopefully you guys got the same thing. Let's do 8. All right, same thing. This leads to 3r cubed plus 8r squared plus 3r minus 2 equals 0. So now you want to be able to try to find the roots of this. You want to be able to factor it, but it doesn't really lends itself very nicely to any previous technique. So now I'm going to look at the possible roots. Now the possible roots of the 2 is 1. Now I'm going to write 1 twice, and 2, write 2 twice. The possible roots of the 3 are 1 and 3. So I get 1 and 3. So these are the possible rational roots. Plus or minus 1, plus or minus a third, plus or minus 2, plus or minus 2/3 are the possible rational roots that I could have for this guy. Now, let's just try to plug in some numbers. Plus 1 doesn't seem, and none of the positives seem like they would work. So let's try the negative. Maybe -1 again. Can we get lucky with that? Works. So if I plug in r equals -1, I would get -3 plus 8 minus 3 minus 2. I think that works. Wow, that's I'm so nice giving all these nice examples. So this means that r plus 1 is a factor once more. You know, the funny thing is, I saw some, there were a time when I gave some examples in class, and it always kind of worked out with one specific number, or did not work out with one specific number. And so when I put a problem similar to that on the test, everyone just assumed that the answer was, oh, it has to be this number is the answer, because every example they looked at had that number. But then I just switched it to the other number as being the answer, just to see, were you paying attention? Did you feel like it's always going to be that number, or were you understanding why it was that number? Yeah, I caught some people with that as well. So so far in all these examples, r equals -1 was working, but probably I'll put something on a test where the -1 is not going to work, but you're going to have people assuming that it does work. It's funny. Students are so funny sometimes. Yeah, so like Kevin is like, it's always either 0 or infinity in Calc 2, right? Like, if when in doubt, what is the answer for the limit? I'm gonna guess 0. No, all right. So let's actually go. R plus 1, 3r cubed plus 8r squared plus 3r minus 2. Yes, just understand, kids, sometimes instructors choose certain examples because they're nice. It's nice to just have a 1 there. So you choose those examples, but it's not because it has to be a 1. It's just the numbers just work out that way here in the examples I chose. Okay, r goes into 3r squared. R cubed 3r squared times, you get 3r cubed plus 3r squared. Subtract this, you get 5r squared. R into that goes 5r. Multiply, you get 5r squared plus 5r. Move this guy down, subtract from the above line, get -2r. R into that goes -2. Get -2r minus 2. Subtract this from the above line. This comes down, and we end up with 0, which we should end up with 0. So this means that my 3r cubed plus 8r squared plus 3r minus 2 is equal to r plus 1, 3r squared plus 5r minus 2. I'm not sure if that factors. So I don't remember. Maybe a 2 and a 1 here, maybe plus and a minus there. It's 3r squared, 6 minus 1. That actually works. This means that the roots are r equals minus 1, r equals a third, and r equals minus 2. Notice that you could have, someone else could have used minus 2. They would have gotten different quadratic here, but it would have factored into these other two parts. It would have factored into the r plus 1 times the 3r minus 1. Similar to up here, the other rational roots were the 5 and the 4, and those were possibilities, right? So if you started out with one of those other possibilities, you'll still get to a point where once you factor everything, you get all possibilities back. So here, we had a third being a possibility. We had minus 2 being a possibility. We had and 1 being a possibility. And look, I got all of them back. Had someone chosen one of these other ones at random to do the long division with, they would have just gotten a quadratic as the result, as the quotient that we call it, and it would have factored into the other two factors. Anyway, this leads us to the solution for this ODE. So this is going to be C1e to the minus t plus C2e to the t over 3 plus C3e to the minus 2t. And hopefully you get that. No, so you can't just plug them all in and assume they're roots. Technically you could, but it's not going to always get you anywhere. If you look at the first example I did, in this one, notice that the roots end up being complex, and they were not ones that I would have guessed in the original list. In my original list does not include them, right? So it's possible that even if you plug in all the guys that appear here, you are not really going to know everybody, right? So you just go one by one. You find one guy that works, then do long division, and then you worry about factoring the other polynomial that shows up. If you like plugging in a bunch of things and calculate, like if you wanted to go through and plug in all of these options, 2, 4, 6, 8, 10, right? There are 10 options here. If you like to just plug in 10 different numbers into a cubic and see how many answers you get, be my guest. But it's possible for it to not work out for most of them except one, if the other roots are complex numbers or something. So my first example kind of threw that strategy out the window, I think. But it is doable. It's something you could try if you have the patience. And if you're hoping that it's going to be a nice case where all three roots are rational, and so they're definitely in this list, and you would prefer to just plug and chug as opposed to doing long division, then yeah, it's an option. But it's possible for it not to work out, and personally, I don't like the plug-in and chugging. Plug-in and chugging one is enough for me. Okay, and that is this method. So, I mean, for me to do any more using this method, it's not really going to teach you anything new. Hopefully that was clear. This is us using the rational roots theorem, and of course, under our breath, the factor theorem to actually factor polynomials and hence solve for their roots and hence solve an ODE. So you see an ODE like this, you can use the rational roots theorem to solve it. So that's another special case. Cases where we need like long division and the rational roots theorem. Another special case, roots of unity. So yes, we did look at this before in some homework, but I am going to show you what is perhaps a more efficient way, or I know, like if you didn't use, this is one of the most efficient ways. If you didn't use this way to do the homework, then chances are you did something less efficient than this. This is a very nice way to do this. And then those are just some more examples. Second, I'm just cleaning some stuff up here. Okay, so special case, roots of unity apply. So what is a root of unity, right? So this is a special term, it's called a root of unity. Let Z be a complex number. It's actually the typical variable to use for a complex number. If you pick up an average complex analysis textbook, instead of using X as the variable, the input, we use Z when we are thinking of the input as a complex number. The solutions to Z raised to the nth power equals 1 are called the roots of unity. And you can also recall that any nth degree polynomial will have n roots in the complex numbers up to multiplicity. This is something that is called the fundamental theorem of algebra. So it's a very important theorem, right? That's the theorem that tells us that we can actually solve. Now, hold on. Let me put that in. This is what's called the fundamental theorem of algebra, right? It's a very important theorem. It's basically the theorem that tells us that any nth degree polynomial will have n roots up to multiplicity. It's basically saying solutions to a polynomial, we are guaranteed to find them, and we know how many of them there are. And that, by the way, this actually helps us in the existence and uniqueness theorem. I'll talk about that later on. So we know that there are answers, and we know exactly how many of them there are. And it turns out, by Galois theory, not always will we have a nice formula to find them, but in theory, they're always out there, and we can approximate them. So that is a very important thing. Okay. Now, what you can do is you can solve this equation using what's called the polar form of a complex number. Now, we say Z is in polar form if it's written in this form, RE to the I theta, right? Basically, if you have any complex number, you can write it. This is called an Argand diagram. This is a complex plane. If this axis here, the horizontal axis is the real axis, that gives you the real part of the number. So that's the A. If I think of a complex number as A plus IB, the A comes from the horizontal axis. The B comes from the vertical axis. This is the imaginary axis. So really, you can think of any complex number as just a coordinate in this plane. Then, if you apply polar coordinates to that, you can pretty much figure out that the A must be R cosine theta, the B must be R sine theta. And so, using Euler's equation, you knowing that e to the I theta is cosine theta plus I sine theta, you can actually express this guy, this complex number A plus IB, in the form R e to the I theta. And that's really you taking into account that because this is going to be R times cosine theta plus I sine theta, which is R cosine theta plus I R sine theta. And you can think of this as the X component. And you can think of this as the Y component, to just use familiar notation. So a complex number X plus IY, I can think of in terms of this form. I can just think of it as R e to the I theta. And it turns out that when I think of it like that, it's actually very convenient to start taking roots, because instead of taking like a root of this guy, the X plus IY, that's a sum. We don't know how to distribute roots across sums. Well, we do know as of Calc 2, it actually expands into an infinite sum. However, it's nicer to take a root of r e to the I theta. And so when we want to look at a root in that way, these equations, which you also derived earlier, also come into effect. They become useful, meaning I can build up any complex number using these four guys, because I can figure out the one as that e to the I2 pi, or more generally e to the I2 n pi. And so if I want some other number, any constant, I can just think of is multiplying by that. So I can think of the number 5 as the number 5e to the I2 n pi. If I want to think of the number minus 5, I can think of it as 5e to the I pi plus 2n pi. If I want to think of the imaginary number, that's e to the I pi over 2 plus 2n pi. If I wanted to think of the number 7i, well, I could think of it as 7 times e to the I pi over 2 plus 2n pi, etc., right? So I can build up any complex numbers from these basic elements. So that's why these guys are important, and I have them here. So let's actually use these guys to solve a root. And you can actually compare this to an example 2, where we had to solve r cubed plus 1 equals 0. This is really solving something like r cubed minus 1 equals 0. But let's say we wanted to do this using roots of unity. So it's just another option for us. So what we can do is we can do the following. Assume z equals to r e to the I theta, and write 1 as e to the I2 n pi. Right? So I'm using this second equation right here. So 1 equals e to the I2 n pi, and z equals r e to the I theta. So then my equation becomes the following. I have r e to the I theta cubed is equal to e to the I2 n pi. Well, then I take the cube root of both sides. This means r e to the I theta would be, well, e to the I2 n pi over 3. Now, there are infinite number of answers that will hit here, but eventually they'll start repeat because you eventually will go around the circle. In fact, this one is going to take like 3 pieces to go around the circle because I'm dividing 2n pi into 3 pieces. So here, we just need to get n equals 0, 1, and 2. And after this, the values start to repeat. After 3 of them, the value will start to repeat. Now you can take any 3 consecutive integers for n, but why not just choose the easiest ones to work with? So that's what we would choose. So yeah, clearly, r equals 1 in the above. And to find the roots, basically now I'm just going to plug in n equals 0, n equals 1, n equals 2, etc. into that number. So if I plug in n equals 0, right? This means 1 root is e to the 0, which is 1. And of course that makes sense, right? 1 cubed is 1, okay? Then I'm going to plug in n equals 1. This will help me find the second root. This is going to be e to the I 2 pi over 3 by just plugging in n equals 1 here. Now, what is that? Well, that is going to be cosine of 2 pi over 3 plus I sine of 2 pi over 3. This is equal to, so you should remember that cosine of pi over 3 is a half. 2 pi over 3 is in the second quadrant. So this is minus a half. plus sine of pi over 3 is radical 3 over 2. 2 pi over 3 is going to be in the second quadrant. So this is radical 3 over 2. So that's my second root. Now, if you go to n equals 2, I know that the third root is going to be minus a half minus this. I don't have to do it because complex roots come in conjugate pairs. And so, finally, I can talk about the solution to z cubed equals 1. Solutions are z equals 1 is one solution, and z equals minus a half plus or minus I radical 3 over 2 are the other two solutions. And there are your three complex solutions. So a complex number, a polynomial, an nth degree polynomial always has n complex roots up to multiplicity. And that's how you can find it using roots of unity. Any questions on that, on what I did? We're going to do some more examples, but so far, are there any questions? Guess not. How did I choose n equals 0, 1, and 2? Pretty much at random. So pretty much what this guy tells me, the two n pi, the 2n pi over 3 tells me that I took 2 pi and I split it into 3 equal sections. So there's going to be an answer 1, 2, 3. The 3 answers will live in these regions. Right? So now, this is just a way to randomly choose 3 regions. I just chose 3 consecutive integers because they'll help me cycle through the regions. I could have chosen any 3 consecutive integers. I could choose 6, 7, and 8, and I would still get the same thing. I could have chosen 7, 8, 9, and I would still get the same thing. I just chose 0, 1, and 2 because they're the easiest ones to choose. So it's almost random, but it's not completely random. I do know I want a bunch of consecutive things. I know I want as many consecutive things as the highest power allows, because that is going to give us, by the fundamental theorem of algebra, it's going to give us enough answers. I know I needed 3 answers here, so I just need to cycle through 3 answers of this guy. And so I just pick 3 consecutive integers to cycle through the 3 answers. And these integers are represented by 0, 1, and 2, but it doesn't necessarily have to be 0, 1, and 2. I could have chosen any 3 consecutive integers. And technically I could have chosen non-consecutive integers too, but I had to make sure that they actually line up so that I'm in the right region, right? So 0 would be equivalent to choosing 3. 1 would be equivalent to choosing 4. And 2 would be equivalent to choosing 5. So I could have chosen 0, 4, and 5, and I would still actually cover all answers as again. Right, so I just chose those because it's the easiest ones to choose. It's the easiest ones to plug in, because eventually I'm going to want to compute things using Euler's equation. So I'm not going to choose some weird numbers. I'm going to choose some very small, manageable numbers. So when I start plugging into these trig functions, it's easy to find the answer. Let's do some more examples. All right, here's a 6th order differential equation. Now, there are other ways to do this. Maybe I should do something else. One thing I want you to note here, we could do the above by difference of cubes. Right, so when I see z cubed equals 1, I could have looked at this as z cubed minus 1 equals 0. And then I could have actually factored that with the difference of cubes. Then I would get z equals 1, or z equals minus b plus or minus a square root of b squared minus 4ac all over 2a. You would get, again, minus half plus or minus radical 3 over 2. Right? So you had other options, but the roots of unity method. So this might even be easier for you to do here. Okay, so you can have more elementary methods to do these, but the roots of unity method is a nice method. So here's an example, another one, a 6th order. And it turns out for this one, again, you could actually use difference of cubes and sum of cubes, but let's actually look at this in another way. I'm just going to choose an example using roots of unity. So here, this would lead to r to the 6th plus 1 equals 0. This means I need r to the 6th equals minus 1. So now what I'm going to do is switch to polar form. Now I already have little r, so let's use big R. Big R e to the I theta to the 6th is going to be minus 1. But my minus 1, remember what my minus 1 is. E to the I pi gives us minus 1. And then I can add 2n pi to that, and it's going to give me the same thing. So this is e to the I 2n plus 1 pi. And so my r e to the I theta is going to be equal to, just take the 6th root of both sides, and I would get I times 2n plus 1 pi over 6. And then I choose 6 consecutive integers. 0, 1, 2, 3, 4, 5, 6. I won't need the 6. Now, I just find all the roots. So the first one, my first root is going to be equal to, when I plug in n equals 0. Plugging in n equals 0, I would get e to the I pi over 6. So this is just going to be cosine pi over 6 plus I sine pi over 6. Cosine pi over 6 is radical 3 over 2. Sine of pi over 6 is a half. And that's my first root. Now for my second root, I plug in n equals 1. Then I would have e to the I. If I plug in 1, I would have 2 plus 1 pi. That's 3 pi over 6. That's pi over 2. This is cosine of pi over 2 plus I sine of pi over 2. And that's just going to be I, because cosine of pi over 2 is 0, sine of pi over 2 is 1. So that's another root. My third, this is when I plug in n equals 2. This would be e to the I, and then I would have 5 pi over 6. So this is going to be cosine of 5 pi over 6 plus I sine of 5 pi over 6. Now, cosine of 5 pi over 6 is going to be the same absolute value as cosine of pi over 6. However, since 5 pi over 6 is in the second quadrant, the cosine gives us negative. So this is minus radical 3 over 2. The sine function, though, is going to be the same because it's in the second quadrant. So it's, again, going to give me a half. Now it turns out that I automatically know the next three, because complex roots come in conjugate pairs. So these guys here are automatically known. Since complex roots come in conjugate pairs. So I just found three very distinct complex roots, which means their other halves need to be solutions as well. So my R4 is radical 3 over 2 minus I over 2. The other one is going to be minus I, and this is going to be minus radical 3 over 2 plus minus I 1 over 2. So that gives me all the 6 roots. So the roots are R equals plus or minus I. Also, it can be radical 3 over 2 plus or minus I over 2. It can also be minus rad 3 over 2 plus or minus I over 2. And so that can help me now find the solutions. So it's going to be C1 cosine plus C2 sine plus C3 e to the rad 3t over 2 cosine t over 2 plus C3 e to the rad 3. I don't know if you can see that. E to the radical 3t over 2 sine t over 2 plus C4 that's a C4. Because I was counting and I realized I wouldn't have gotten 6. So this is C5 e to the minus rad 3t over 2 cosine t over 2 plus C6 e to the minus rad 3 t over 2 sine t over 2. And that's that guy. It's worth mentioning, once again, we could also use more elementary means. Because this one happens to be something that's nice that we can break down into cubes and squares. So whenever you have something that you can break down into cubes and squares, It might even be more worth your while to use things like the difference of squares and the difference of cubes and the sum of cubes to your advantage. If you don't have something like that, then it's a little bit harder. So you might have something like an r to the 5th plus 1 equals 0, in which case it's definitely not, while you could factor that by more elementary means, it's going to be very hard to find some of the roots, to find 4 of the roots in there. So this method is definitely better there. But here, we could actually do something differently. We could actually say r to the 6, what was it? R to the 6 plus 1. So if I see r to the 6 plus 1, I could just think of this as r squared cubed plus 1 cubed. And so this sum of cubes would be r squared plus 1 times r to the 4th minus r squared plus 1. And then this guy here is going to give you the plus or minus I. This guy here, you can use quadratic formula. R squared is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And you would have gotten the other two, or the other 4, actually. Right, so you could have done it that way. So I mentioned here that you could do a lot of these the other way, so I just wanted to show you guys what that would have looked like. So I don't want you guys to think that the homework was unfair and there's no way you could have solved it if Jhevon didn't teach us about roots of unity. Gave us that homework. But you could have solved the problems without it. The algebra would be a little bit more annoying, but it was possible. Let's do other basic techniques. Other basic techniques involve doing things like just like creating generic factored forms. So for example, random example. I should probably preface this, like, I'm never actually going to ask you a question where you would need this, but outside of this class, you might need something like this. But FYI, so suppose, because it actually may come up in the homework. In fact, the reason why I have the urge to do this is I feel like once upon a time in a semester long ago, a student showed me a homework problem that none of the techniques that I showed in class could solve the problem. And this was the technique that they should have used. So I don't know, I don't remember if it was a web work problem or it was a problem from the textbook. But I know that there was a problem where none of these techniques worked. So in case you hit up one of those guys in the homework, you can try this. So a random example. So I'm gonna make up a random example. So like x to the 4th minus 3x cubed plus 5x squared plus 2x minus 7. Right? So here's how you can think. You just think of generic factors. So for example, you have x to the 4th minus 3x cubed plus 5x squared plus 2x minus 7. It's a fourth degree polynomial. So technically by the fundamental theorem of algebra, this guy can factor into 2 quadratics. The quadratics might have complex roots, but it's possible to factor them as quadratics. So what you can do is you can actually just write it out like that. You can write it out like, okay, ax squared plus ax plus b, and then I can have like x squared plus cx plus d, right? Or you can even go and factor it as x minus a times x minus b times x minus c times x minus d, or something like that, or x minus a times x minus b times x minus c times x minus d. But the idea is going to be the same. Now, what we can do is we can multiply out. And I know the coefficients of the square terms have to be 1 because the coefficient on this side over here is going to be 1. But if the coefficient here wasn't 1, then you need generic coefficients in front of the both x squares. But anyway, I can take the x squared from the first guy and multiply out. So that's going to give me the x to the 4th plus cx cubed plus dx squared. And so that's me taking the x squared in the left pair of parentheses and multiplying out the right pair. If I take the ax from the left pair and multiply out the right pair, I would get ax cubed plus acx squared plus adx plus, now take the b, bx squared plus bcx plus bd. And so now I would have, let me move the chat box out of the way here. Now I would have something like x to the 4th plus, let me group the cubes, c plus a x cubed. Let me group the squares, d plus ac plus bx squared. Let me group the x's, plus ad plus bcx, and let me group the constants, bd. And so now what you can do is you can equate coefficients. So I can just match up the coefficients on the left and on the right. And so basically I would get a plus c must be minus 3. Then for the square term, it should be 5. So ac plus b plus d should be 5. The linear term should be 2. And the constant term should be minus 7. Then solve the system. Which I'm not going to do because solving such a system is going to be annoying in general, but I just wanted you to see an example. So you could actually do a generic, you can multiply all these guys out or multiply all those guys out and kind of just match up the coefficients. Okay, so that's just another technique that was out there. Just so you know, just for your education. Can't say Jhevon never told you. All right, so here are some examples, which, I don't know, I doubt anyone actually solved them, so try these for next time. So use what I taught you today, get those out of the way, and we'll try those for next time. What I want to do with the remainder of the time is go back and actually justify the way that things have been working heretofore. So right now, you know a bunch of techniques for solving higher order differential equations, various ways to like factor and solve the characteristic equation. And then picking up from there should be relatively straightforward, just taking into account things that we've looked at before. Just to make sure that you can actually do it, I really want you guys to go, because I've been talking this whole time. I don't even know if any of you are following me or if any of you even did the problems that I did. So make sure you try them, right? Because it's coming up on the quiz next week. So let's get some practice in. What I want to talk about now is I want to explore the existence and uniqueness theorems. And we're going to talk about pretty much the linear cases. And I will talk about the nonlinear case of the first order tomorrow, as well as finish up those examples that I just asked you to finish up. So right now, I'll give you some time to like take a snapshot of this, take a picture. 5, 4, 3, 2, 1. Okay, so make sure you take those pictures. Make sure you actually solve them. You need to be an active participant in your education. It's better for you that way. Now, yeah, we are going to explore the existence and uniqueness theorems. Today we're doing the linear ones. Right, so there are a bunch of things that I was telling you that we've, for the most part, taken for granted. The fact that an nth order linear differential equation will have n linearly independent solutions if it's homogeneous. And if I take a linear combination of those solutions, then that would give me the general solution to that. And then if there's a non-homogeneous case, then just adding adding a particular solution to this will actually give you the entire solution. And this solution is going to have this uniqueness to it. Not only will it for sure exist, if the coefficients are continuous, for sure we can find a solution to that. But we know we can find one. We also know it's unique, and we know how many of them there are. How can we know all this? That's what I want to actually talk about today. So it's going to be a little bit theoretical, but at the end, I have one concrete example that I want to work through with you guys so that you can actually see this being done in practice. So essentially, I'm going to use linear algebra to solve a second order ODE. And a human being wouldn't do this, but I'm just going to show you what I'm going to justify can be applied to the kinds of examples we've been working on. And if you want to justify it, or maybe you're asking a computer to be able to solve ODEs, it's actually better to program it this way because computers love working with matrices. All right, so here's the usual disclaimer. I'm going to talk about a lot of technical things, a lot of abstract math, a lot of linear algebra and all that stuff. And I am aware that a lot of you just haven't covered the requisite mathematics to actually fully understand what I'm talking about. So for the most part, I'm going to be very hand-wavy. More or less, while it is going to be somewhat technical, I'm really going for an intuitive explanation here, where hopefully you can kind of see how things all fit together, even though you might not know specifically the mathematics that's going in behind the scenes. You can kind of see, oh yeah, I see why this math would lead to that math over there, even though I don't know exactly how. So it's not going to be very comprehensive. It's not going to be super technical, and it might not even be technically correct in some scenarios, the things that I'm writing down, but it's just to give you an intuitive feel. And we're going to start with the basics. What is an operation, right? So I'm going to be mentioning the things all the time. An operation is just a way of combining two or more elements of a set to get some other elements. So for example, addition is an operation. You can think of addition as I can take a number, combine it with another number, and I get a third number. If I take 2 and combine it with 3 using the operation addition, the result is the number 5, right? So an operation is just a way to combine elements to create another element. An operation that we combine two elements at a time is called a binary operation. Shouldn't be operator. It's called a binary operation, okay? Operators are other things as well. These are guys that can act on one element at a time to create something else. So for example, differentiation is an operator. You can talk about the differential operator, right? It's just an operation. It acts on one thing and then it outputs one other thing. So for example, I can take the differential operator with respect to x, hit x squared with it, and then, or probably more appropriately, yeah, hit x squared with it, and then the result is going to be 2x. So it operates on one polynomial and it outputs another polynomial. A field. Now, a field is a set that has two, in which are defined two binary operations. We call these guys multiplication and addition, and it's closed under these operations, which means when you add two elements of the set, you get a third element of the set, and if you multiply two elements of the set, you get another element of the set. And these properties actually hold, right? So basically, addition is associative, addition is commutative. There exists a number 0, quote unquote, which if you add it to anything, you get back the thing. Every guy is going to have a negative where it's if you add it to the original, you get the additive identity. Multiplication is associative, multiplication is commutative. There exists a number that we call the multiplicative identity, represented here by 1. It doesn't have to be specifically 1 all the time, but it's represented by 1, such that if I multiply any element by that guy, I get the same guy back. For any non-zero element, there is an element called the inverse, or the multiplicative inverse, such that if I multiply the element by that, I get the multiplicative identity, which is 1, and the distributive law holds. Moreover, if I have some operation, and I really should have put the less than or equal to in quotes here, if I have some operation for which these guys hold, I say that I have an ordered field, right? So these are the above properties of something that's called a field. Now, some of you might know what a field is. The real numbers, for example, form a field, right? So the set of all real numbers with usual addition and multiplication form what is called a field. They behave, they obey all these properties. Now, in a field, there are some things that you might have taken as being obvious, but they're actually not obvious. Properties like the following, right? So if A plus C equals B plus C, that means that A equals B. In other words, that's what tells us that we can add something to both sides of the equation and not change it. If I multiply anything by 0, I get 0. If I take the negative of something times something else, I can factor off the negative. A negative times a negative is a positive. If I have A times C equals B times C and C is not 0, I can cancel the C's and get A equals B. If A times B equals 0, then either A equals 0 or B equals 0. We take these things to be obvious, but they're actually not. You can actually prove these things here by using these properties up here. So these are the properties that define something, a set like the real numbers, and these are consequences of those properties. By the way, the members of a field are what we call scalars or constants. And again, when you hear scalar or constant, everyone tends to think real numbers, but it's actually more general than that. They don't have to be real numbers. For us, yeah, every time I say scalar, I really mean a real number, but it can be a more general thing. So the intuition here for you guys, if you want to think of these guys with a little more concrete example in mind, is of course the real numbers. The set of real numbers with addition and multiplication form a field, right? So that's your referential example. So basically a field is any set that behave like the real numbers behave, with two operations that you can think of as analogous to addition and multiplication, right? But it doesn't have to be the real numbers. It can be anything else. The rational numbers also form a field, right? So the set of all fractions would form a field. The set of complex numbers would form a field. By the way, the set of integers does not form a field. How do I know the set of integers cannot be a field? So I cannot think of the set of integers as technically constants if I'm only thinking of them as belonging to the integers. The integers are only considered constants if I think of them as members of the real numbers. The reason is because of M4. M4 fails with the integers, right? And one way you can see this is that, well, division is not going to work. Not everyone has a multiplicative inverse. So for example, if I have the integer 2, what can I multiply that by to get the identity 1? Well, I'd have to multiply it by a half, but a half is not an integer, right? So I cannot find an element that would turn, that when I multiply 2 by, I would get 1. So the integer is not a field, right? So it's not just any set of numbers forms a field. It's a very special kind of set that would have these properties. The real numbers have these properties, and the complex numbers have this property. The rational numbers have this property. The integers do not. So yeah. So just to make it easier for us, from now on, because we're in a calculus class where we're dealing with real and complex numbers, you can think of constants as referring to real numbers, and you won't lose anything by that. The next thing is a vector space, right? So a vector space is a set of things called vectors, and it has two operations, addition and scalar multiplication. Addition is a way to combine two vectors to get a third vector. Scalar multiplication is a way to combine a scalar from a field and a vector to create another vector. A vector space must fulfill these 10 properties, right? You don't need to memorize what those properties are, but they should be familiar if you actually start to read them. The set of scalars, the field that we're using, if we have a specific field in mind, we say that the vector space is a vector space over that field, right? So I can talk about a vector space over the real numbers. All right. So intuition, like do I know an example of this? Yes, you do. The set R3 that you learned about in Calc 3 is in fact a vector field. Think of the set of three-dimensional vectors and all the things you could do with them. They actually form a vector space, right? So that's a concrete example you can have in your mind. Anything that behaves like R3 behaved back in Calc 3, we call a vector space. And it doesn't have to be vectors in the traditional sense. It can just be anything that behaves like that set of vectors that we had in Calc 3, right? For example, the set of matrices with complex entries form a vector space, right? So they don't have to look like vectors. Polynomials form a vector space, right? So for example, I can look at a polynomial like a quadratic here, and I can just imagine it as a vector. And it turns out I can do everything with this vector that I could do with this polynomial, and no one would tell the difference mathematically. You won't be able to tell the difference. It looks different when I write them down, but it's not actually different. I can go through and with the properties that I have from R3, play around with quadratics by thinking of them as 3D vectors, and everything will work out the same way. Now, here's the thing. The set of solutions to a differential equation is a vector space, and that is very important. If you look at the set of solutions to a differential equation, you will notice that it will obey all these 10 properties. And that's why we can now start thinking of these solutions to differential equations as vectors. And then we can start putting these vectors inside of bigger structures and thinking of them as matrices. And then we can use matrices to get a lot of things from linear algebra to apply to our solutions to differential equations. So hopefully you guys see where this is going. The usual definition of linear combination and linearly independent I have here, you guys actually know that. Kramer's rule is going to come up again, and I think you guys remember Kramer's rule. I even introduced it in this class. Not going to talk about that again. Just getting through the preliminaries. These are the things you need to know about fields, vector spaces, and linear combination, linear independence, and you need to know Kramer's rule. So let's actually jump in, finally. So let's look at the existence and uniqueness theorem for first order linear ODEs. So if I have an equation of this form right here, where the P and the G are continuous on some open interval I, then it turns out on that interval, I can find a unique solution to this differential equation. And if my T naught is any number in that set, in that interval I, then if you give me any random initial condition, pick a solution that when I plug in T naught, it's your favorite number, I will be able to choose arbitrary constants in my general solution that is going to fit that number that you just gave me, right? That is called the existence and uniqueness theorem for first order linear ODEs. An equation like this is guaranteed to have a unique solution that will fit any initial conditions that you give me. And it's going to exist and it's going to be unique. meaning anyone who comes up with any other solution, either they're wrong or their solution is equivalent to mine. You just have to simplify it, right? So that is what allows us to do things like, oh, let's guess that this is a solution to this ODE. And then when it works out, we can say, oh, that's the general solution. Like, how would you know that this random thing you guessed is the solution? Well, I know because of this theorem. This theorem tells me that there is only one, which means no matter how you find that one, that is going to be the only answer. So yes, guess if you want to guess. If it works out, then that's exactly the guy that you wanted to find, right? Now, how can you prove this? It turns out that understanding why this is true is not hard, and actually proving why it's true is not hard. It's actually the method of integrating factors, which you guys know very well. Actually doing the method of integrating factors, I can tell you exactly down to a formula what the unique solution to this is, right? It's going to be the integral of like mu times g all over mu, right? Where there's going to be an arbitrary constant of integration that you have to also divide by mu. And the mu, I know what that is. That is e to the integral of the p. Now, in theory, these integrals will always exist for continuous functions, although in practice, it might be very difficult to actually find them. But in theory, they do exist because it's continuous. So the fundamental theorem of calculus tells us that it should be there. Now let's talk about something like a system of linear ODEs. This is going to be very important. And this is going to be important to the nth order case. So we actually know the first order linear case. There's nothing else to actually talk about that. To deal with the nth order case, I want to talk about systems of first order cases so that you can understand how the nth order case is going to work out. So suppose I have two functions that I can take their derivatives and they conspire into a linear system like this. Okay, so let's just pretend it's a linear system of differential equations. I can write these in terms of matrices like this. And if I write vector y prime as this and just vector y as this, I can write the system as that. Vector y prime equals this matrix times that y. Now this looks like a first order linear equation, which means we know that it has a solution, right? I can apply this theorem, I can apply the above theorem to this. The above theorem applies. So this has a unique solution, right? Because now it just looks like first order, right? It's like instead of a constant, I have a matrix, but again, it forms a vector space. It's all going to work out, right? So now let's actually look at a way, how would we go about solving this, right? You make a guess. I know I can make a guess because there's a unique solution. As long as my guess works out, it's fine. What would you guess? Well, remember when I asked you on day one to guess a solution to y prime equals y? And when you guessed it, an exponential seems like a good guess. Well, for the same reason, an exponential seems like a good guess here. Let's guess that the solution looks like some vector times an exponential. Right? I know it's a 2D vector because I have a 2 by 2 system and my y is a 2D vector here. So my solution should also be a 2D vector, but let's suppose it's a two-dimensional set of exponentials. What would this mean? Well, if I were to differentiate this vector, I would get something that looks like this, right? So I think of it as a constant times e to the lambda t. Differentiating means multiplying by lambda. So I get this as the answer. Now, if I plug into this guy, I get this. My exponential is not 0, so I can divide both sides by it. And I can also factor out the lambda from here. So I end up with this kind of statement here. Now, if I set x equals this guy, mn, and set a equals this, I end up with this kind of thing, right? This looks exactly like that. This is lambda x equals a times the vector x. Now, does that equation look familiar to anybody? I've been talking for a long time. Let's see if people are still alive and breathing out there. Have we seen something like that before? Ax equals lambda x. I know at least two of you should definitely know what that is. right? So two of you have been in 392 at least. I know two of you told me you took 392 already. That was what you did to the end of 392. That was what was called an eigen, remember? This is when you wanted to find the eigenvalues and eigenvectors of a matrix A, right? So in 392, we told you that we can solve for this, and then it actually solves an ODE, a system of ODE. And then they're like, you never really explained why a set of eigenvalues and eigenvectors can be used to solve a system of ODEs. They just told you that the answer is given by the eigenvalues and eigenvectors. Even when I taught 392, I didn't tell my class why the eigenvalues and eigenvectors solve a system of ODEs. But here you're seeing why. It's because we pretended a solution looks like an exponential, and then when we plug in the matrix answer, it's simplified into a situation where solving that situation is equivalent to finding the eigenvalues and eigenvectors of a matrix. That gives you this right here. So yeah, it's the equation you use to find eigenvalues and eigenvectors of a matrix. Those of you in 392 will know exactly what I'm talking about. Those of you taking that. If any of you are currently in 392, towards the end of the semester, you're gonna see this guy here show up, and you will have a new appreciation for that equation. No one in your class is gonna know where it comes from, but you will know. So for now, I'm going to assume that you know how to solve the above. The vector x solution to the above is called an eigenvector, and the lambda solutions, where lambda is a constant, these guys are called eigenvalues. We're interested in a non-trivial solution. Hopefully you know how to find those. 392 would teach you about that. If you don't know that, you don't remember, or you haven't taken 392 and you're interested, here's a link to my 392 video where I actually teach people how to actually do that. So here's the upshot. We can always find a solution to the above system. So if I have a system like this, right, I would always be able to find a solution. I know one exists by the existence and uniqueness theorem for first order linear differential equations. And by using eigenvalues and eigenvectors, I know I can actually have a method to actually find this solution, right? I know I would actually find that, I can find that solution. And yes, to Insha, if you took the new 346, they probably do that there. They do this there as well. The old 346 doesn't have it. All right, so the idea is if I have such a system, I can always solve it. Also, at this point, you can know that there are going to be two solutions because you will have an answer for the m and the n. There are only going to be two exponentials that can solve this. You can know that the second order, there are only going to be two because you are working in 2D. You can't have three, you can't have one, you have to have two. It has to be exactly two because you're working in 2D. So it's like when someone says, oh, is there a third solution linearly independent for a second order linear differential equation? The answer is no. That's like you asking me, can a two-dimensional vector have a third component? No, it can't. It also can't have one. It can't have five. It can't have seven. It has to have exactly two. So I know a second order linear differential equation has to have two solutions because I can reduce it to a situation where I'm working with two-dimensional vectors. Right? So that's kind of why we have to have n solution. It has to be exactly n, meaning if you find less than n, you're missing someone. If you find more than n, then either you're completely wrong or you're linearly dependent with one of the other guys. You have to be able to reduce it to n, right? The reason is because we can actually get a matrix out of it. And I'm going to show you specifically how to get a matrix for a higher order pretty soon, right? And now it's worth mentioning that this I showed you for a 2x2 system, but it can work for a larger system as well. And just so you know, that a system like this, I can always solve it uniquely. This is combining what I know about eigenvalues and eigenvectors combined with the existence and uniqueness theorem for first order linear ODEs, right? And this, of course, is the homogeneous case. I'll deal with the non-homogeneous case later on. Because if there's going to be plus some other vector here if it's the non-homogeneous case, right? So it can work with 3x3s, 4x4s, 5x5s, all that stuff, right? So let's look at the nth order case, right? This is the preliminaries for the nth order case. right? So I have an nth order linear differential equation. I want to, then it turns out we're guaranteed to find a unique solution of this form that will solve this equation with any set of initial conditions that you find, right? How can I get to use this situation, right? Because I'm going to want to use this situation. Because mathematicians from time immemorial, when you want to solve a complicated problem, one of the first things you try to do is reduce it to a simpler situation that you already know how to solve. Here's how we can reduce this to a simpler situation. I can take this single equation and I can transform it into a system of linear equations in the following way. Relabel. Call my y, y0. Call my y prime, y1. Call my y double prime, y2, and so on and so forth. All the way up to call my nth derivative of y, y sub n. Then that means if I move these guys to the right side, I can write my nth derivative in this form, right? Where now there are no derivatives there, at least notation-wise, there are no derivatives. You can line up these equations, y equals y naught, y prime equals y1, y double prime equals y2, etc. And these guys just beg to be thrown into a system of equations, so you do that. When you throw them into a system of equations, this is what you can kind of get. If I hit the differential operator on this vector, the derivative of y is y prime, the derivative of y prime is y double prime, derivative of y double prime is y triple prime, etc. That gives me this. Now my y prime, I relabeled as y1, my y double prime relabeled as y2, y triple prime relabeled as y3, etc. All the way down to the yn. My yn, as you can see in the bottom of this vector down here, is just this entire list right here. That came from the fact that I just brought everyone over to the right side. Now, via matrix multiplication, I can write this huge matrix as this matrix times that. Notice that you can kind of see like an identity matrix here being formed. And then on the bottom of the list is just the coefficients of the original ODE. And then on the right side, I just have all my functions being listed as they have been relabeled, right? So ultimately, I can get to this system of equations. Now, I can relabel them again. I can call this guy over here, call this y, call this guy here a, and then call this guy over here y prime, because it is in fact a derivative of a set of functions, right? So I can actually relabel all of these guys. I don't know if I should leave those markings. Maybe I'll leave them. Now, what happens when I relabel all those guys? I end up with this system. So I just went from an nth order linear differential equation to a first order linear system. I know from the above that that system has a unique solution, which means I can solve this system uniquely. The solution is going to look like this, right? And I can find a unique vector that will solve that. And guess what? The first component of that vector is going to be my solution to the original ODE, because my y is the y naught. So I can actually solve a system by linear algebra, right? I can take an nth order linear differential equation. I can create a first order linear system just by relabeling the derivatives. Once I get to there, I can use my existence and uniqueness theorem for first order linear differential equations to actually show that I have a unique solution. I can use eigenvalues and eigenvectors to guess what that solution is and actually compute it. And I would get the answer. Now, the above works in the homogeneous case. To get the non-homogeneous case, just think of the vector 0, 0, 0 going all the way down to g, and I can add it here. And then because I know I can find the homogeneous solution, I would just use the integrating factor method to find a solution to this. And in fact, you'll realize that you will get a YP being added, whose formula looks a lot like the variation of parameters formula. Remember, we use a bunch of matrices to derive that formula. Put that all together, and boom, you have the existence and uniqueness theorem for nth order linear ODEs. And it's something that we can get from linear algebra. And it's like, how can we know that it had n solutions? How can I know that they're linearly independent? How can I know that there are n of them and that they combine into form a solution like this? Linear algebra is how I know. This is how I know. So yeah, that's actually it. Now, I actually skipped a lot of hand waving. In a typical textbook, it would take many pages and many chapters to give you the same amount of information that I'm giving you right now. So it is going to be, again, very hand wavy, but I think hopefully a little intuition, you can see intuitively why these things connect and conspire to find a solution in the way that we have found them. By the way, once I finished typing that up, I realized that we never actually fully explained why it is that given a random set of initial conditions, anyone can pick a random set of initial conditions. I can take my general solution and find coefficients that will solve, that will match my unique general solution to a random set of initial conditions. So here is where I illustrated for second order linear differential equations, and that's pretty much because I couldn't bother typing out some big matrices like this, just to make it a little less cumbersome on myself. So why is it that given any set of initial conditions, if I can find a general solution, I can find constants, arbitrary constants that will fit it? Well, suppose I have a solution y equals c1y1 plus c2y2 to some second order linear differential equation. And suppose someone gave me some random initial conditions, y of t naught equals y sub 0, and y prime of t naught equals y prime of 0. Y prime is sub 0. Then if I take my general solution and differentiate it, I would get that. And then if I plug in our initial conditions, I would get these two. Notice that I can put these in a matrix like that. And you will notice that the determinant of the coefficient matrix here is just the Wronskian of the original solutions, which means because it's a solution and I know it's unique and they're linearly independent, it actually has a non-zero determinant, which means this solution has a unique solution. This system has a unique solution for C1 and C2. That follows by Kramer's rule. And so that's how I can know there's going to be a unique choice of C1, C2, C3, etc. that is going to fit any random set of initial conditions someone gives me. Because when I throw it into a system, Kramer's rule forces me to be able to solve for and find a unique solution. And so that's how I know that not only can we have a unique solution, but given any set of initial conditions, as this mentions here, and that the general thing mentions here, given any set of initial conditions, I can find a version of my solution, a unique version of my solution that will fit those initial conditions. Right? It follows by Kramer's rule. Now what I want to do, finally, is to actually use the linear algebra way to solve a system, a second order linear differential equation with constant coefficients. Everything I said earlier would actually work even if the coefficients were not constant, as long as they're continuous functions, by the way. So now I'm going to actually solve this using the linear algebra way. We know how to solve it in a different way, but the linear algebra is the machinery in the background that gave us the power to actually do that. So of course, we're going to be very appreciative of the linear algebra, even though we never actually use it in practice, but I actually want to see it. And so you guys are going to see how you would actually apply the things you learned in 392 come together to solve an nth order linear differential equation. So right now you can watch me, because you're never going to have to actually do this, and I'm never going to require you to actually do this. I just want you to, I've been talking very quickly through all this theoretical mumbo jumbo. And if you missed all of the theoretical mumbo jumbo, I want you to have some concrete example to look to see how it actually would work out. Can that really work out, or is that just some theoretical mumbo jumbo? Well, here's an equation that you can actually find the solutions for pretty easily using methods that I previously taught you. I'm going to use the above theoretical machinery to solve this ODE. How would I go about getting the system? Well, set y equals y1 and y prime equals y2. this gives me some immediate things. If I take y1 prime, I would get y2. And if I take y2 prime, I would get the y double prime. So now, notice what I would have. Also, y double prime is equal to 4y prime minus 3y, which by the above notation is just 4y2 minus 3y1. And so this leads me to the following scenario. I can line these guys up. If I look at y1 prime and y2 prime, that is just going to be, well, my y1 prime is y2, and my y2 prime is going to be y double prime. This is going to be equal to y2, and then the bottom one is going to be 4y2 minus 3y1. So now, this is going to be equal to, you will notice it's 0y1 plus 1y2, and down here I have 4y2 minus 3y1. And so if I have this, essentially would become, if I look at it as y1, y2, and this over here is going to be y1, y2 prime, I would be able to write this as 0, 1, minus 3, 4. So if I think of this as my y prime, this as my y, this as my matrix, I get that system that I spoke about. Now I know that the solution to this is given by y is going to be equal to some constant times lambda 1 vector e to the lambda 1 t plus some other constant lambda 2 vector e to the lambda 2 t, where lambda 1, lambda 2 are eigenvalues of A, and the lambda 1 vector, lambda 2 vector are the corresponding eigenvectors. So now we're in the land of 392, where I think, if most of you have seen it, if you've taken the new linear algebra 346, you would have seen it there. If you've taken 392, you definitely saw it there. So we would go about finding the eigenvalues and the eigenvectors of this vector. So here A is going to be 0, 1, minus 3, 4. So to find eigenvalues, we need to solve the determinant of lambda I minus A equals 0. So this means I would find the determinant of lambda minus 0, minus 1, 3, lambda minus 4, set that equal to 0. What you're going to realize now is I find the determinant of that set equal to 0. And by the way, just so you can keep your bearings, gasp. At this point, you should be gasping, because that's actually the characteristic equation. By the way, in linear algebra, it's also called the characteristic equation, which is why in ODEs, we call it the characteristic equation. Now I'm going to go through and I'm going to, so you can see the solutions to this are the guys that I'm going to plug into the powers of the exponential. And now it makes sense where those guys are coming from, hopefully in hindsight, if you go back and reread the notes that I have here very slowly. So here we would go and we would try to solve this, I think -1 and -3. So we get lambda equals 1, that's one solution, and lambda, the second solution is 3. Now you go to find corresponding eigenvectors. You can solve lambda I minus a times x equals the 0 vector for each lambda above. So now, when I plug in the lambda into this up here, I get for lambda 1, it's going to look like 1 minus 1, 3 minus 3, 0, 0. That would simplify to 1, 0. I'll get 0, 0, 0 here. This comes from row 1 times 3 minus row 2. So here my x2 would be, say, q. And x1 would also be q. So my x1, x2 would be the vector q, 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 q. So that is the eigenvector. Similarly, I can do this for lambda 2. This is going to look like 3 minus 1. It'll actually be the same in the other part if I plug those guys in. This is 3 minus 1, 0. Bottom is 0, 0, 0. This is a dependent system. This I can take by row 1 minus row 2. Set a parameter equal to the column that doesn't have a leading 1 in it. Call this R. Then I would get 3x1 equals R. And so then I get my x1, x2 in this scenario to be R over 3 and R, or in other words, R times 1/3 and 1. And I'm gonna scale this just to make it nicer. This is equivalent to multiplying, just scaling by 3, 1 and 3. And I'm going to use this as the second eigenvector. And so this means the solution is my y, which is the same as y1, y2, is c1, 1, 1, e to the 1t plus c2, 1, 3, e to the 3t. Notice that this means that my y1, y2 is going to be c1 e to the t plus c2 e to the 3t, and down here it's going to be c1 e to the t plus c2 3c2 e to the 3t. And if you look along that first line, you get what the y1 is. So y is equal to c1 e to the t plus c2 e to the 3t. And that's the solution, right? So that's how this linear algebra, all this theory I was talking about, how you would actually apply it, how it looks when you're actually hitting it with a concrete example is like this. Relabel the guys so that you can put them in a matrix. Solve that matrix using techniques that you learn in something called spectral theory, where you study eigenvalues and eigenvectors of various kind of matrices. You can solve that, and you'll realize that you just take the first line from the matrix solution, and that's going to be the solution to your ODE. Right? And so that's how the theory would have worked. Now, of course, in general, no human being would solve it this way, right? However, to prove why we could solve it the way we solved it, this is what's happening in the background. Of course, we don't think of it this way, but this is actually why things work out the way it works out, how we know that there are only two answers, how we know that there has to be an answer, how we know that it's going to be unique, how we know it's going to be able to fit, we can get that solution to fit any set of initial conditions. It's all linear algebra. We can think of these functions as vectors and actually use matrices to talk about all this stuff. Anyway, at this point, we're way over time, so let's wrap up there. Hopefully that satisfied some of your curiosity. You won't ever have to actually solve a problem like that, but you do need to know how to solve what we did earlier. So try solving these for tomorrow's class. Tomorrow I'm going to talk about first order nonlinear existence and uniqueness theorem, go over some examples, and then we'll go over some of these guys. But for now, we are going to stop there. So that's it for today, guys. Remember, your next quiz is next week, Tuesday. It'll be on everything that we've done since the test. And I guess we are going to... Oh, to answer Ophir's question, I don't know. I would reach out to the registrar's office. I know you guys do it. I can't do it for you. Reach out to the registrar's office. I think there's a way to do it in CUNY first, but I don't know where to go because that's a new thing. And I never did that. So if any of you guys want to talk about any of those grades that like the no credit or anything like that, you want to see the registrar's office. They'll tell you how to do it. Anyway, I'll see you guys later. And I guess that's it. Be safe. And I'll see you in the next one. So, ciao.